There's nothing like a hot, nice cup of coffee on a cold night. Well, I was tutoring a few students at the university a few days ago in physics, and we came across this question from one of the previous year question papers on physics 2, I think electromagnetics. And I thought it would be a great video to put on. It's a nice practice review to go over. So the question goes like this. There are three current carrying wires, current carrying conductors basically, 1, 2, and 3. And there's a point P at a distance D, which can also be considered as the radius of a circle if you make this look like a circle basically. And the point P basically subtends an arc of 45 degrees. Uh, if you look at it the other way, I mean, the conductor 2 is in the shape of an arc, which subtends an angle of 45 degrees at the center of the circle. So the question is to find out the magnetic field caused by conductor 1, 2, and 3 at P separately. And the fourth part of the question asks you to find the net magnetic field caused by this setting, right? So, and these conductors are carrying current in the direction shown by these arrows, right? So, this way, here, and then here, right? So, pretty simple. Before we go to solve the first part, let's actually go over the formula we need to solve this problem. We need the Biot-Savart formula. And till today evening I thought it's called Biot-Savart, but then when I referred to the textbook called University Physics by Searson Zemansky, they've written that it's pronounced Biot-Savart. So nice to know, right? So the Biot-Savart law gives us the magnetic field at a point as given by this, right? So mu naught over 4 pi times I times dl, cross product with the vector which represents the direction at which the point is present, right? So this is r. So basically, if you see, this is r, right? So I'll draw expanded views each time we need them, but for now it's just that. So if we again solve this, what we get, the cross product of any two things is just those two things. This basically is a unit vector, so you'll get dl sine theta, where theta is the angle between the current carrying conductor and the unit vector, right? So as simple as that. So the first part we need to find, or a part, we need to find the magnetic field at point P caused due to conductor 1. So if we look at it and we refer back to this formula, look at this. Conductor 1 is this, and r cap vector is here, right? So the angle between them, I mean, they're parallel, so the angle between them is 0, right? And sine of 0 is 0. So the entire term becomes 0. So the magnetic field at P due to 1 is 0, or 0, null, zilch, right? And now due to 2, right? So let's redraw 2 here. That's a nice curved little thing, and we have a 45-degree angle in between, and this is point P, and the radius of this little arc is given by d, right? So, and let's write the formula here again. So mu naught over 4 pi I times dl cross r over r squared, right? So here, if you see dl, what would it be? even if you consider a small part of this thing, this basically makes an arc, right? So it's an arc length. Our conductor is an arc length. So dl is given by d times radius times the angle, right? So for dl, for a small part of that length, let's consider d theta, right? And this cross product will produce a sine, let's call it phi because it's a different angle function. But if you look at sine phi here and consider small infinitesimal part here, right, and the angle it has with the r cap vector, it will always be 90 degrees at each point. If you see, right, if you consider probably a million infinitesimal parts of this arc length, basically that length is like a tangent, right, to the circle. And if you draw the radius back there, the radius always subtends an angle of 90 degrees. I mean, has an angle of 90 degrees with the tangent to a circle, right? So sine theta is always going to be 1, sine 90, right? So it's always going to be 1. So we're not going to include the sine theta value when we're solving for this. So the rest of them remain the same, right? Instead of r, we're just going to substitute d here. I hope I'm not confusing you. So we can get the magnetic field at point P due to 2 with this formula. Mu naught I over 4 pi. For dl, we're going to write d times d theta. Don't get confused between this d and this d. This is the radius. That's what they've given us, right? And this d theta is a part of the angle, basically. And the distance, basically, is again r squared, right? I mean, r squared can be written as d squared, so d squared, right? And we got to integrate this. Everything else remains constant, just the theta is going to change, right? So it's going to go from 0 to pi over 4 radians. 45 degrees is pi over 4 radians, right? So, oops, yeah. This now looks like this. B equals mu naught I over 4 pi d. D theta, theta going from 0 to pi by 4. That's all it is. So this is just mu naught I over 4 pi d times pi over 4. Right? So pi cancel. So it's just mu naught I over 16d. It would really help if you just go back there to the top where I started working on the second part of the problem and trace back what we did, and then it'll also help to pause this video and do it by yourself so that you get a better understanding. It's always better to work on paper than to just look at a video and go, you know, yeah, this is pretty simple. It'll be really helpful if you could not see what I did and work it by yourself and get the same result. Okay? Alright. So we're also going to talk about, they also want the direction of the magnetic field at P. Right. Before we go to that, because it'll be a slightly different concept to look into. Let's work out the magnitude of magnetic field at point P due to conductor 3. Okay, we come back to the previous the diagram of the problem. Again here, even if your r cap is here, you know, and 3 is here, they're anti-parallel, which again means they're 180 degrees apart, and sine 180 is 0. So your magnetic field at point P due to conductor 3 is going to be 0, right? It's as simple as that. They're parallel or they're anti-parallel. The magnetic field, because of them, is going to be 0, right? So we have magnetic field only due to 2 at point P, right? So A is 0, B is mu naught I over 16d, and C is 0 again, right? Now we have to work on D, which is the total, the net magnetic field at point P. It's pretty simple. The net magnetic field is just 1 plus 2 plus 3. Like the magnetic field's due to 1 plus that due to 2 plus that due to 3, which is again the same thing as mu naught I over 16d, right? So Not a big deal. Now, we have to talk about the direction of magnetic field at point P due to 2. I mean, everything else is 0, right? So let's talk about that due to 2. And I'm seriously bad at drawing. I should have listened to my mother when she asked me to pay attention in art class, but I never did. So here I am struggling in front of you.